Hello everyone, I am Vinayak Shinde. Today I am going to compare the deep residual network or ResNets with the traditional plain deep learning for image recognition. We will be using the CIFAR dataset. We will be exploring the Microsoft research paper, a groundbreaking paper which introduced the ResNets from 2015, which has over 250,000 plus citations. So let's dive into it and see what is the plain deep learning, how it was going in before versus the residual or the ResNets. So you might be wondered like why Microsoft made ResNets or residual deep learning for image recognition. What was the main cause behind that? So we are going to check that what why they made. So traditionally in the plain neural networks or the plain convolutional networks, what was the issue like when the input is passed to the neural networks which have deep layered structure, which have deep layer, the depth is more. Each neuron which has the random weights which it multiplies to the activation function. What happens then if the network is so deep, then this goes on up till end, and at the end we don't have the thing which we have to go to predict, like the input is missing. The thing which we have is only the random noise. And also while doing the gradient descent, at the initial gradient descent, while going backwards, also we have the same random noise because we have lost the input data while randomly multiplying to activation functions. So to cure this thing and adding some accuracy and perceiving the input data up till end of the output to predict it, the Microsoft team made this. This is a deep residual learning or ResNets. They have done simple but yet more powerful thing which saved a lot of things, which is now inspirations for the new technologies, the new Gemini's nano banana. This is the main core technology because of which the nano banana is there. So let's dive like how they done. So what they did is after they divided each layer or a group of layer into a batch or a blocks. Okay. So what was the task like? After every batch or every block, they added the input with the correspondent output of each layer. For example, here the input is x and the layer has given output of f of x. Then they added that, means x plus f of x. Now this x plus f of x is given as an input to another block, and this goes on at any depth. So what is the benefit of it is like now we have the input of x in every iterations in every blocks. So at the end our the input data which we have to predict, we have that data just by simply adding it. So this was simple but yet so powerful. So we can compare here what was the difference. See, I will just show you first this. This is a plain versus a ResNet over 20 layers. But in the 20 layers, we can, it is negligible. But if you increase the layers, if you go to 56 layers, then we can see significant differences. This is only 56, but if you go to 156, 256, 356, then the differences are humongous. This was the paper which was published by Microsoft Teams. They have compared with 20 layer versus 56 layer architecture of this plane and the residual ResNet which they performed. So I won't waste my time. Now let's dive into the code while comparing both. First, let's set up our environment. We will install PyTorch, Torch Vision, and TDQM. The reason for the TDQM is to show the progress bars. The device is now set up in CUDA. We are using the T4 Tesla 4 from Google Colab, which is easily available, which speeds up our training. Okay. We will load the CIFAR 10 with the 60,000 32 into 32 images across 10 classes. The paper uses these data sets, as you can see in the paper, which is show in the degradation of 56 layers. We apply transformer like paddings and flipping for the trainings, matching the paper's data augmentation to improve the robustness. So now let's build the blocks. The plain block, the basic block, and the ResNet block. What are these three? The plain block is a simple two-layer convolutional ReLU structure which is used in plain networks. It processes the input directly with no shortcuts. See the forward pass. The basic block, yeah, I have wrote it first, but the reason I will explain. The basic blocks is for ResNet. It adds a shortcut connection which is like x plus f of x. This matches with the paper's figure 2. We can see here where the input x skips the ahead and sums our output, which is f of x, solving the degradation problem by easing the gradient flow. Now, we will define our models, both PlaneNet and ResNet. Start with a 3 into 3 convolutional layer. Now we have three stages with filter 16, 32, and 64. Downsampling each stage. The key difference is the number blocks, which is equal to 9 into 9, a single row matrix, which giving 56 layers according to the paper's table for 1. The ResNet uses basic blocks with shortcuts, while the plain network uses the plain block without the shortcuts. Okay, so now this is the training. Now the train function uses the cross entropy loss and the SDG with momentum of 0.9 matching with the paper's optimizer. We log the loss as per epoch using the TQDM, which filed for progress bars. We log the loss and the accuracy per epoch using TQDM. The test function evaluates without the gradient, logging the test matrices. And this our LR. It drops by LR means learning rate scheduler. The learning rate scheduler drops by 0.1 at epoch 80 to 120. Approx. Now our training loop will run over the 200 epochs, which is used, and I will be running this for 20 layer structure and 56 layer structure, just to explain like what will be the difference if we increase the number of layers. So now our training data is here. Now, finally, we are going to visualize this. Okay. Here, for the 20 layer structure, the comparison between the ResNet and the plane, it shows like there is no big gap between both. Like there is a very negligible similar gap. Okay. Same the loss function. But if you check for the 56 layer architecture, the 56 layer, then the gap is visible and it is quite big. Accuracy which we got is like for plane for 20 layers. I am saying first for 20 layers we got 90.84 for plane and 91.95 for ResNet, like 1% difference between both. But for the 56 layer structure, we got 86.71% accuracy for the plane and 93.23 25% accuracy, which is like 6 to 7% of 6 to 7 percent gap between both. Okay, so this gap between both will surely increase if we increase the models layer. Like now it is 56, we can go to 156, 256. This can go increase. In here is
Now
our I have compared the every epoch by epoch, every 20 epoch difference for the plane and the ResNet for 20 layers and the 56 layer. In 20 layers again, there is no much gap. Like we can't, it is like negligence. Like, but in the 56 layer, we can observe clearly like there are many gaps. Like in first 20 epoch only, the ResNet given like 86% of accuracy approximately, and the test, the plain test, it gave like 43 or 45%. This was you gap between the first epoch and the last epoch. There is like 4 to 5% of gap. Here is our convolutional matrix for both, and we have finally compared between both, like how this new technology, I can't say new because it is like 10 years old, but this smart move by Microsoft team just added tons of accuracy in this research work. So that was from my side. I tried my best to explain this concept. I think there might be some point where my explanation is not on point, but I will improve myself in futures. Thank you. Thank you for watching till end.